In this lecture video, we'll be going over some of the basics of hypothesis testing. The most basic element of a hypothesis test is the hypothesis, which is a claim or statement about a property of a population. A hypothesis test, then, or test of significance, is a procedure for testing that claim about that property of a population. In order to conduct a hypothesis test, we'll need to take the information from the hypothesis and figure out what the null hypothesis and alternative hypothesis should be. The null hypothesis, denoted H0, is a statement that the value of a population parameter, such as the proportion, mean, or standard deviation, is equal to some claimed value. The term null is used to indicate that there is no change, or no effect, or no difference. It's equal to some claimed value. On the other hand, the alternative hypothesis, denoted H1, is a statement that the parameter is a value that somehow differs from the null hypothesis. This will be a statement that involves a less than, greater than, or not equal to symbol. Let's take a look at a few examples and see if we can state the hypothesis as a claim and also determine the null and alternative hypotheses. Let's start with example A, which reads, "It has been reported that young adults spend an average of 4 hours per day playing Call of Duty Modern Warfare. A random survey of 15 students revealed a mean of 5.5 hours with a standard deviation of 2. The surveyor claims that the amount that these students spend playing Call of Duty is significantly more than young adults on average. Using a 0.05 level of significance, what should the college student conclude?" We are not actually going to conduct this hypothesis test, but rather we're going to write the claim in words, then symbolically, followed by the null hypothesis and alternative hypothesis. In this paragraph, the claim is located here. These students spend more time playing Call of Duty on average than all young adults. Now to write this symbolically. We're told that young adults on average spend 4 hours playing Call of Duty. So if the claim is that these students spend more time than the average young adult, we could write this as mu, the mean, since we're talking about an average, is greater than 4. The null hypothesis must be a statement of equality. We must state that the population parameter, in this case the mean, is equal to some value. With the context of our claim, the appropriate null hypothesis, H0, is that the mean is equal to 4, that there is not this significant difference from 4 hours. The alternative hypothesis, H1, is not a statement of equality. It needs to be less than, greater than, or not equal to. It is important that our claim is represented in either the null or alternative hypothesis. It's not represented in the null hypothesis, so we'll make sure to include it here. The alternative hypothesis will be the statement that the mean is instead greater than 4. Let's take a look at another example. Example B reads this. According to the Pepsi Challenge, 73% of Americans have at least a favorable opinion of the soft drink Coca-Cola. Alejandro randomly surveyed 40 college students and found 34 students favor Coca-Cola. He claims that the proportion of college students who favor Coca-Cola is significantly different than the general population at a 0.05 significance level. In this example, the claim is found here, and we can state it with words like this. The proportion of college students that prefer Coca-Cola is different from 0.73. To write this symbolically, we'll use a letter P since we're referring to a population proportion. And notice that it's not being claimed that the proportion is greater than or less than 0.73, but simply that it's different from 0.73. So we can state this claim symbolically as P is not equal to 0.73. With our null hypothesis as a statement of equality, we should write H0 as the statement that the proportion is equal to 0.73. Now the alternative hypothesis will reflect our claim. H1 is the statement that the proportion is not equal to 0.73. Let's take a look at one last example. Example C reads this. It is thought that teenagers sleep more than adults on average. A study is done to verify this. A sample of 16 teenagers has a mean of 8.9 hours slept and a standard deviation of 1.2. A sample of 12 adults has a mean of 6.9 hours slept and a standard deviation of 0.6. What should you conclude using a 0.05 significance level? In this example, we can find the claim here, and it's important to notice that we are comparing two populations in this case, rather than comparing one population parameter to a fixed value. We can write our claim in words like this: teenagers on average sleep more than adults. We are comparing the mean of one population, teenagers, to the mean of another population, adults. So to write this symbolically, we might write something like mu1 is greater than mu2. Our null hypothesis will still be a statement of equality. We could write H0 as the statement that mu1 is equal to mu2, that there does not appear to be a difference between the two population means. The alternative hypothesis in this case will reflect our claim. H1 will be the statement that mu1 is greater than mu2. Now we need to add some more vocabulary surrounding hypothesis testing. Alpha is our significance level. It's the probability value used as the cutoff for determining when the sample evidence constitutes significant evidence against the null hypothesis. In other words, we let the null hypothesis stand as true unless proven otherwise. By its nature, the significance level alpha is the probability of mistakenly rejecting the null hypothesis when it is in fact true. In other words, we could write that the significance level alpha is equal to the probability of rejecting H0 when H0 is true. Common choices that are made for alpha are 0.05, 0.01, and 0.1, just like we saw when we were constructing confidence intervals. Let's start drawing some pictures. With our hypothesis testing, we will need to know how to handle a right-tailed test, left-tailed test, and a two-tailed test. With a two-tailed test, alpha, or the significance level, is split into the two tails. With a right-tailed test, all of alpha is in the right tail. And with a left-tailed test, all of alpha is in the left tail. Let's learn some more vocabulary and add it to our pictures. The test statistic is a value used in making a decision about the null hypothesis. It is found by converting the sample statistic, such as p-hat, x-bar, or s, the sample proportion, mean, or standard deviation, to a score, such as z, t, or chi-squared, with the assumption that the null hypothesis is true. The critical region, also called the rejection region, is the area corresponding to all values of the test statistic that cause us to reject the null hypothesis. Let's add these to our picture. The space in the one or two tails determined by alpha is also called the critical region. What separates the critical region from the rest of the distribution is called the critical value. With a right or left-tailed test, we have one critical value. And with a two-tailed test, we appropriately have two critical values. When we translate our sample statistic into a test statistic, that test statistic may or may not land inside the critical region. Let's take a look at our two-tailed test. If our test statistic were to land somewhere like this, then that means it's not inside the critical region, also called the rejection region, which implies that we would not reject the null hypothesis. But if instead the test statistic was here, then it would be inside that critical region and it would cause us to reject the null hypothesis. One hypothesis test method involves comparing the location of the test statistic and the critical value. If the test statistic is more extreme than the critical value, then we would move to reject the null. If the test statistic is not as extreme as the critical value, then we would not reject the null. Let's continue adding more vocabulary. Next, we have what's called the p-value, or probability value. This is the probability of getting a value of the test statistic that is at least as extreme as the test statistic obtained from the sample data, assuming that the null hypothesis is true. This is the area that corresponds to the location of our test statistic, which brings us to the hypothesis testing method called the p-value method, and that's where we compare the p-value to alpha. Let's add this to our picture. Let's use our left-tailed test to add this to our drawing, and suppose that our test statistic is right here. The p-value is the area or probability associated with the tail cut off by the test statistic. So in our picture, it's this left area here. With the p-value method, we compare the p-value to alpha. Notice that when the test statistic is not within the critical region, the p-value, or area in this tail, is more than alpha. But notice that if the test statistic were on the other side of the critical value in that critical region, the p-value would be smaller than alpha. The two methods are equivalent. Whether you're comparing the locations of the test statistic and critical value, or comparing the areas, the p-value and alpha, you will end up with the same result. You will either reject the null hypothesis or fail to reject the null hypothesis. That concludes this lecture video where we talked about the basics of hypothesis testing.